We're really going all in on this one.
That's exciting.
It is. You wanted to understand this fundamental particle, so we're going to break it down. Are you ready to kind of explore the universe at its smallest level?
Absolutely. I think a good place to start is with the question, what gives everything mass? Why are some particles heavier than others?
Right, yeah.
And this is really where the Higgs field comes in. So imagine this invisible energy field. It kind of permeates all of space.
So not like a physical substance, but more like a property of the universe itself?
Exactly, exactly. And as particles move through this field, they interact with it. And it's this interaction that gives them their mass.
Oh, okay.
So some particles, like the top quark, interact very strongly with the Higgs field and become very massive, while others, like electrons, interact weakly and remain relatively light.
So it's kind of like, I don't know, like walking through mud versus walking on pavement. Some particles experience more resistance and become heavier.
Yeah, that's a good analogy.
Okay.
But here's the really interesting part. The Higgs boson itself is the quantum excitation of this Higgs field. It's like a ripple in the field, a direct manifestation of its existence.
And this ripple, this Higgs boson, is what scientists at CERN finally detected, right? Back in 2012.
Yeah.
July 4th, to be exact. Quite the fireworks show for physics.
It was a monumental discovery. And, it took decades of theoretical work in the construction of the Large Hadron Collider, which is the world's most powerful particle accelerator.
Right.
And by smashing protons together at nearly the speed of light, they were able to create the conditions necessary to produce the Higgs boson and then observe its fleeting existence.
You say fleeting existence. Why doesn't the Higgs boson stick around for very long?
Yeah, so the Higgs boson is incredibly unstable, and it decays almost instantly into other particles. It's these decay products, these specific combinations of particles that scientists were looking for to confirm the Higgs boson's existence.
So you're talking about decay channels.
Yeah.
It's like the Higgs boson has a unique fingerprint.
Right.
And these decay channels are like the individual ridges that allow scientists to identify it.
Precisely. So the Higgs boson can decay into different combinations of particles, like pairs of photons or pairs of W or Z bosons, or even pairs of bottom quarks.
Okay.
And these specific decay channels, they're like the Higgs boson signature. And by observing them, scientists can be certain they found the particle.
So just to clarify, the Higgs boson doesn't decay randomly. It follows specific patterns determined by, its interactions with other particles.
Exactly.
And the laws of physics. And these patterns are crucial for confirming its existence.
Yeah. And these decay patterns, they also tell us a lot about the Higgs boson's properties, such as its mass.
Speaking of mass, I remember reading that the Higgs boson has a mass of about 125 GeV. That number doesn't really mean much to me.
Sure, yeah.
Could you put it into perspective a little bit?
Yeah, so 125 GeV, it means it's about 133 times heavier than a proton.
Okay.
Which is one of the particles you find in the nucleus of an atom. So it's a heavyweight in the world of subatomic particles, but still incredibly tiny compared to, say, an apple.
Okay, yeah. That helps. It's fascinating to think about something so small having such a huge impact on the universe. So we've talked about the Higgs field, the Higgs boson, its decay channels, and its mass. What else makes this particle so special? Why is it considered one of the most important discoveries in the history of physics?
Well, besides giving mass to other particles, the Higgs boson also plays this crucial role in the unification of the electromagnetic and weak forces.
Oh, okay. So
Yes.
two of the fundamental forces of nature, the forces responsible for electromagnetism and radioactive decay.
Exactly. And before the Higgs mechanism was proposed, these two forces seemed completely separate, unrelated. But thanks to the Higgs field, we understand that they are actually two different aspects of a single unified electroweak force.
So the Higgs boson isn't just about mass, it's about unifying forces. Like it's like this tiny particle is the key to understanding the fundamental structure of the universe.
That's right, yeah. It's a key piece of the puzzle physicists have been trying to solve for decades. But even with this discovery, there are still mysteries to uncover. And some of them are even more mind-boggling.
Oh, okay. Now you've got me hooked. What kind of mysteries are we talking about? What lies beyond the standard model of particle physics, and how does the Higgs boson fit into this bigger picture?
That's where things get really exciting. We're talking about concepts like dark matter, supersymmetry, and composite Higgs models. And the Higgs boson might just be the key to unlocking these mysteries.
Sounds like we're about to take a deep dive into the unknown. I'm ready. Lead the way. Okay, so we've established the Higgs boson. It's fundamental, right? to the universe. But you mentioned dark matter, supersymmetry. Those sound like concepts out of science fiction.
Well, they might sound like it, but they're very real areas of active research in physics.
Okay.
So let's start with dark matter. We know that everything we can see, stars, planets, galaxies, makes up only a tiny, tiny fraction of the matter in the universe. The rest is this mysterious substance we call dark matter. It doesn't interact with light, hence the name dark.
So we can't see it, but we know it's there because of its gravitational effects on the visible universe.
Exactly. Galaxies rotate faster than they should based on the visible matter alone. So scientists think there's this invisible stuff holding them together.
Like an invisible scaffolding for the universe.
Yeah.
So some physicists think that the Higgs boson might be our key to understanding this invisible scaffolding.
That's one of the most exciting prospects. Yeah. Some theories suggest that the Higgs field might actually interact with dark matter particles, giving them mass, in a similar way to how it gives mass to other particles.
Oh, wow. So it's like the Higgs field is a universal mass giver, not just for the particles we know and love, but for this mysterious stuff lurking in the shadows of the universe as well.
Yeah, precisely. And this brings us to another intriguing concept, supersymmetry,
Okay.
or CUSY for short.
CUSY.
This theory proposes that every particle in the standard model has a superpartner, a particle with the same properties, but a different spin.
Oh, so every particle has a secret twin, and we haven't found any of them yet.
Not yet, but the search is on. CUSY predicts that these superpartners exist at higher energy scales than we can currently reach with our colliders. And if we find evidence for CUI, it would not only validate the theory, but also potentially solve another big puzzle, the hierarchy problem.
You mentioned that earlier, but I'm still a bit fuzzy on what the hierarchy problem actually is. It sounds kind of ominous.
It is, in a way. The hierarchy problem basically boils down to the fact that the Higgs boson's mass, as we measure it, is surprisingly light
Okay.
compared to what our current theories predict.
So, see, the Higgs boson's mass is incredibly sensitive to quantum fluctuations.
Yes.
Those tiny random fluctuations in energy that happen even in a vacuum.
And according to the standard model, these quantum fluctuations should make the Higgs boson much, much heavier than it actually is.
It's like expecting a feather to weigh as much as a bowling ball.
Exactly.
So it's a problem because the Higgs is defying the laws of physics by being so lightweight.
Essentially, yeah. And this suggests that there might be something missing in our understanding of particle physics, something that stabilizes the Higgs mass and prevents it from being inflated by those pesky quantum fluctuations.
And supersymmetry could be the answer. Like, by introducing these super partner particles, we could potentially cancel out those troublesome quantum corrections and keep the Higgs mass stable at a lower value.
That's the idea. It's like those super partners are acting as bodyguards for the Higgs boson, shielding it from the chaos of quantum fluctuations.
Ingenious. But you also mentioned something called composite Higgs models. How do they fit into all of this?
Yeah, so composite Higgs models offer an alternative solution to the hierarchy problem. They propose that the Higgs boson isn't a fundamental particle at all, but rather a composite particle made up of smaller, more fundamental constituents.
So instead of being like a single, indivisible entity, it's more like a tiny machine built from even smaller parts.
Yeah, that's a great way to put it. And in these models, the mass of the Higgs boson is determined by the interactions between these smaller constituents, not by those troublesome quantum corrections that plague the standard model.
So the composite nature of the Higgs would naturally protect its mass from being inflated by those quantum fluctuations.
Exactly. It's a completely different approach to solving the hierarchy problem, and it has profound implications for our understanding of the fundamental building blocks of the universe.
So we have two competing theories, supersymmetry and composite Higgs models, both trying to explain the Higgs boson's unexpectedly light mass. It's like two different teams of detectives trying to solve the same mystery using different clues and methods.
And the best part is we don't know which team will crack the case first, or if there's an entirely different solution waiting to be discovered. It's this sense of mystery and the constant pursuit of knowledge that makes physics so captivating.
Speaking of captivating, I can't help but wonder. We've talked about the Higgs boson's role in the present-day universe, but what about its role in the very early universe, right after the Big Bang?
Oh, that's a fantastic question. It takes us back to the very beginning of time, to a moment when the universe was incredibly hot and dense, and all the fundamental forces were unified.
You're talking of a time when the universe was just a fraction of a second old.
Exactly. And in those first fleeting moments, the Higgs field played a crucial role. As the universe expanded and cooled, the Higgs field underwent a dramatic phase transition.
A phase transition, like water freezing into ice.
Precisely. It's a sudden change in the state of a system. And in the case of the Higgs field, this phase transition caused it to switch on throughout the universe.
So before this transition, the Higgs field was dormant, and then suddenly it became active, like everywhere. What triggered this sudden change?
Yeah, it's a question that physicists are still trying to answer. But the implications are profound. It's this switching on of the Higgs field that gave particles their mass. And in a way, it's what shaped the universe as we know it.
Without this phase transition, the universe would be a vastly different place, perhaps devoid of stars, galaxies, even planets.
That's a very real possibility. The Higgs field is so fundamental to the structure of the universe that even slight variations in its behavior could have had dramatic consequences for the evolution of the cosmos.
This is all so fascinating, but I have to admit, it's a lot to take in. We've gone from the Higgs boson's role in giving mass to particles to its potential connections to dark matter and supersymmetry, and now we're talking about its influence on the very fabric of space-time.
And we're just getting started. The Higgs boson is like a gateway to a whole new realm of physics. And there are still so many mysteries waiting to be unraveled.
Well, I'm ready to keep exploring. What other insights await us on this deep dive into the Higgs boson? So we've journeyed to like the edge of our understanding of the universe, but the quest for knowledge never really ends, right?
Right.
What are the next steps in this adventure? Where do we go from here?
Well, that's where the Large Hadron Collider comes back into the picture.
Okay.
While the initial discovery of the Higgs boson was, a monumental achievement,
Yeah.
it was just the beginning. Scientists are using the LHC to study the Higgs boson's properties in really exquisite detail,
Okay.
hoping to uncover even more secrets about this enigmatic particle.
It's like finding like a rare artifact. The initial discovery is thrilling, but then the real work begins.
Exactly.
When we try to decipher its inscriptions and unlock its hidden meanings.
They're measuring its mass, its spin, its decay modes, how it interacts with other particles with incredible precision. And these measurements are crucial because they let us test the predictions of the standard model of particle physics.
Okay.
Which is, the framework that describes all the fundamental particles and forces we know of.
So it's a way of double-checking our understanding of the universe.
Yeah.
Looking for any inconsistencies that might point to new physics beyond the standard model.
Precisely. And even the slightest deviation from the standard model's predictions could be a sign of something truly revolutionary.
Okay.
A hint of new particles, new forces, or even new dimensions.
New dimensions. That sounds like something straight out of like a science fiction novel.
It might sound fantastical, but the idea of extra dimensions is a serious topic of research in theoretical physics. Well, some theories propose that our universe might be embedded in a higher dimensional space, and the Higgs boson might be able to interact with these extra dimensions, leaving, subtle traces in its behavior that we could detect.
So by studying the Higgs boson, we're not just learning about, a single particle. We're potentially opening a window into like entirely new realms of reality.
That's the beauty of science. It's this constant exploration pushing the boundaries of what we know. And the Higgs boson is really at the forefront of this exploration. It's a key that could unlock some of the universe's deepest secrets. And who knows what incredible discoveries await us, right?
I have to admit, I started this deep dive with like a vague understanding of the Higgs boson, but now I'm seeing it as this incredibly profound entity connected to so many fundamental aspects of the universe. It's like the Higgs boson is the linchpin holding everything together.
That's a great way to put it. The Higgs boson isn't just a random particle. It's, woven into the fabric of the cosmos, influencing everything from the formation of galaxies to the very nature of space and time.
It's truly humbling to realize how much we still don't know about the universe.
Yeah.
It's a reminder that the quest for knowledge is never ending, and there will always be new mysteries to unravel and new wonders to discover.
And the most exciting part is that we're living in a time of, unprecedented scientific progress.
Yeah.
With the Large Hadron Collider and other cutting-edge experiments, we are constantly pushing the limits of our understanding. And who knows what groundbreaking discoveries await us in the years to come.
Yeah, I for one am eagerly waiting to see what the future holds. You know, the Higgs boson has opened up a whole new realm of possibilities, and the journey has just begun.
And that's the beauty of science. It's a journey of exploration, discovery, and wonder. And the Higgs boson, with all its mysteries and complexities, is a perfect example of how the pursuit of knowledge can lead us to a deeper understanding of ourselves and the universe we inhabit.
So, to our listeners, we encourage you to keep exploring, keep asking questions, and keep that spark of curiosity alive. The universe is full of wonders waiting to be uncovered. And who knows, you might just be the one to make the next groundbreaking discovery.
Until next time, keep diving deep into the world of science. The adventure never ends.